I'd like to welcome everyone to this afternoon's seminar. And it's a real pleasure to introduce Professor Susanna Widicus Weaver from Emory University. Susanna is a native Midwesterner, received her undergraduate degree at Illinois Wesleyan, moved to Caltech for her PhD with Jeff Flight, a postdoc at the University of Illinois with Ben McCall, and has been now a faculty member at Emory, rising through the ranks with promotion to professor. The ink is almost dry on the documents at this point. So Susanna has this training in chemistry, molecular spectroscopy, and astrochemistry and astronomy. And so this afternoon she's going to tell us about complex chemistry in regions of star and planet formation.
All right. Thank you, Bob, and thank you everyone for having me. I know there are people here from both chemistry and astronomy, so my talk's going to be a mix of the two, but I'm hoping to give you enough background that everybody can follow along. So I'm an astrochemist. My group is interested in looking at how molecular complexity evolves as stars and planets form, and we do that from a combination of laboratory work and observational astronomy and some astrochemical modeling. And I always like to start with this picture. This is actually sunrise over the summit of Mauna Kea from the front of one of the telescopes that I've used for a lot of the work that I've done in my career as an astrochemist. And if you could pan around over the summit, Keck would be right here. To give you perspective on this picture. So we study star and planet formation from a chemical perspective. Most people in astronomy use molecules as probes of temperature and density, and kinetics looking at velocities and motion and objects in space. I'm a chemist. All of my degrees are in chemistry, and so I use observations and physical constraints of the interstellar regions where we see molecules to try to understand the chemical mechanisms at play. Space is very, very different than what we have here on Earth, even the most extreme environments. We had this conversation at lunch with the students. Even the very best ultra-high vacuum on Earth is not as good as the vacuum in space. So I want to walk you through these different types of regions and give you perspective on the physical parameter space that we're working with, and we'll talk a bit about how that influences the chemistry. So this is the very famous Hubble Space Telescope picture of the Eagle Nebula. The Eagle Nebula is an interstellar cloud, which is comprised of gas and dust. The dust particles in these clouds are on the order of microns in size. They're mostly silicates and carbonaceous, amorphous carbon in nature, and they're coated with a few monolayers of water ice with a little bit of other stuff embedded in the ice. Reggie Hudson from NASA Goddard Space Flight Center says everything else is dirt. There's water and there's dirt. We're dirt. And so these clouds are where new stars are formed, where these gas and dust particles actually undergo gravitational attraction and collapse to form a new star. So if we walk through the regions of space to give you perspective, on Earth at sea level, the density is about 10 to the 19th molecules per cubic centimeter. Of course, room temperature is 300 Kelvin, and we're 10 to the 11th meters away from the sun. One arm of the Eagle Nebula, one talon on the Eagle, is 10 to the 16th meters across. So 5 orders of magnitude bigger than the distance between us and the sun. The diffuse interstellar medium, the stuff between the clouds, between the stars, is about 10 molecules per cubic centimeter. This is primarily atomic and molecular hydrogen. And it's about 50 Kelvin because there's quite a lot of ionizing radiation in those regions. In the dark, cold clouds, where things are shrouded from the radiation from new stars and cosmic rays can't make it through, dense interstellar clouds go up in density to about 10 to the 3rd, but down in temperature to about 10 Kelvin. And so it really limits the chemistry that can happen in these regions because at 10 Kelvin, everything's frozen out in that water ice on the dust grains, and nothing moves except for atoms at 10 Kelvin. But if you warm it up just a little bit, as a new star starts to form, the chemistry gets interesting really quickly. So there are these regions called hot cores, and out on the edges of the Eagle Nebula, you can see these little wisps. that's where new stars are forming, and they're starting to burn off the gas and dust around them and etch out their own solar system within that region. These are called hot cores because they're about room temperature. They're a few hundred Kelvin. The density is up to 10 to the 7th because this is collapsed gravitationally, because it's where a new star is forming. And it is in these regions where we see chemistry start to look a lot like terrestrial chemistry. So all the organic molecules you use in organic lab in undergrad, methanol, ethanol, acetic acid, acetone, all of those sorts of things all start to show up in these star-forming regions. So it's fascinating to me as a chemist that as we walk closer and closer to a star forming and planets forming, the chemistry becomes more and more terrestrial. And so my group tries to understand those processes and what we can learn about these environments, and hopefully someday get chemical clocks of the star formation process from the observational information that we obtain. What I'm really interested in is how we go from simple molecules like water and methanol up to molecules that would be considered biologically relevant. How do we build sugars and amino acids in the interstellar medium? Can we build sugars and amino acids in the interstellar medium? So the big key research questions for my group are: how far can the chemistry go in space? How does the physics affect the chemistry in these varying environments? And then at what stage does biologically relevant chemistry turn on? So if you look at the processing of material in the interstellar medium, you go from these clouds into young solar systems where there are comets and there are meteorites and there are asteroids and there are planetesimals. And at that point, you have condensed phase processing of material. And we know that we have amino acids and sugars in those objects, but we don't know if we can form them out in space or if we have to have that condensed phase chemistry to get to that next step in molecular complexity. And then eventually that material gets delivered to an Earth-like planet and could jumpstart the formation of life. We know that up to 100% of the water on Earth was actually delivered from cometary impacts in the early days of Earth's formation. And a lot of organic molecules have been found in comets, and so we think that a lot of that precursor to biology could have actually been delivered through those sorts of those impacts. And so my group is trying to understand how we build a molecule like glycine if we start from this very simple chemistry in space and work our way towards planets. We do this through a variety of methods. We do laboratory spectroscopy. We do astrochemical models where we do kinetics networks of thousands of reactions, and we actually change the physical conditions and run the network as a function of time. And then we also do observations. Really, everything in this field started from the observations. And then the laboratory spectroscopists had to figure out what all those lines were coming from. And then all of it goes back into the astrochemical models. So each branch of astrochemistry relies very heavy on the other areas. Most people that work in this field work in one or two of these areas and collaborate for the rest. My group is one of the few that actually has active research in all three areas of astrochemistry, because we want to see the big picture and link it all together. All of our measurements are done in what's called, for astronomers, the far infrared. For chemists, the terahertz regime. If you like wavelengths, this is millimeter and submillimeter spectroscopy. Pick your favorite unit. So I have all of them up on the scale. So chemists, I have wave numbers up here just for you. So we're in the 10 to 100 wave numbers range. 1 millimeter to 100 microns, or 300, well, a few hundred gigahertz up to a few terahertz in frequency space. This is traditionally called the gap in the electromagnetic spectrum. Optical techniques like you would use for laser spectroscopy don't always work in this range. We don't have sources that work from the generation of light in that way, though that is coming. And the microwave techniques that were built off of the radar technology from World War II, for the longest time, were limited to about 100 gigahertz. Now, because of telecommunications and security applications, all of that is pushing up in frequency space, which is amazing for my lab, but terrifying for radio astronomers because of radio frequency interference. So this terahertz gap is starting to close, and it's actually right now the heyday of molecular astronomy, because we have a lot of far infrared observational facilities that have opened up this range. And a lot of the technology I use for my lab spectroscopy came from leftovers from these 3 observatories. So the first is the Herschel Space Observatory. It was a joint mission between NASA and the European Space Agency. It had a 5-year lifetime till it ran out of cryogens and warmed up. It was out in L2 orbit past the moon. Herschel was the far infrared version of Hubble. Herschel, we are still mining Herschel data. I have unpublished Herschel results that we will someday figure out, hopefully. So Herschel really transformed the field. SOFIA is a plane-based observatory where there's actually a telescope behind this door. They fly in the upper atmosphere, open the hatch, and point the telescope out the plane. And then ALMA is now built in Chile. ALMA is an array of 66 radio antennas working in conjunction to take not only molecular spectra, but also images of the interstellar medium. So if you understand, like if you look at a Hubble Space Telescope picture, ALMA has that sort of resolution at these wavelengths, and every pixel has its own broadband molecular spectrum embedded behind it. And so it's now up to us as laboratory spectroscopists to catch up with the data rate in astronomy. This was never the way that it was in the field, and really astronomy's moved into astroinformatics in the last 10 years. ALMA puts out 300 terabytes of spectra a week. So we have a huge challenge as spectroscopists to keep up with that and try to build the tools that we need to be able to analyze that. As a chemist, this region is particularly interesting because these windows in the terahertz regime probe pure rotation of small molecules, rho vibration of large molecules, and all the torsional modes of molecules with internal motion within the molecule. And so it gives us a direct structural fingerprint of the molecule, and we can actually pull out quantitative temperature and density information from that. So when we go and take a spectrum of space, we know exactly which molecule we're looking at, and we can measure temperature and density directly from that rotational spectrum. So in the lab, it's our job to get those spectra so that we can go and look for those molecules in space. As I said, I'm interested in understanding the chemical mechanisms that happen in these regions and how we build molecular complexity. And everything in astrochemistry is driven by kinetics rather than thermodynamics. So if you think about those densities, it takes about 1 million years for 2 molecules to find each other and react in an interstellar cloud. And the only reason that interstellar chemistry gets interesting is because there are a lot of ions in the interstellar medium. 99% of the universe is hydrogen. So pretty much once the molecules come off the grain surface, they get protonated. And once we have ions, if there's a dipole moment, the ion-dipole attraction speeds the reaction rate up enough that you can actually get reactions to go fast enough to build molecular complexity. Before that, the molecules in the condensed phase actually undergo bombardment from either cosmic rays or direct UV photodissociation. They break into radicals. Those radicals react and build up some level of complexity in the ice. Every time we think we've figured out how far that chemistry goes, somebody does a new experiment and we start all over again. So it's actually really exciting in the field right now to see all the new chemistry coming out of ice experiments. But if you couple these two together, it's really radicals and ions that drive the chemistry of space. So it's transient molecules, things you can't buy in a bottle, that drive the chemistry of space. And so I've built my research group around the concept of increasing the capabilities of spectrometers so that we can study those molecules you can't buy in a bottle. So I'm going to talk a little bit about my laboratory work, and then I'll move over into some of the astronomy that we do. We have a lot of different projects in my lab, all of them geared at looking at different aspects of astrochemistry, and in particular trying to find molecules that either directly trace the ice chemistry or the gas phase chemistry, one or the other. So we do a lot of different projects. The one that I'm going to talk about today is this first one where we make reactive organic molecules using the insertion reactions of excited oxygen atoms. Basically, we get creative with the chemistry in the lab so we can make the things we think are there in space so that we can go and look for them. The second project, photolysis branching ratios, we're actually trying to measure what happens in space. But by and large, the chemistry we do in the lab has very little to do with what actually happens in the interstellar medium. We're just after the end products of that chemistry. We look at molecular ions. We look at, recently started looking at gas phase molecules ejected from ices when we photolized them. Basically, we're trying to build a comet in the lab. Houston's over there. Houston's senior honors thesis was building that experiment. And then spectra of star-forming regions, of course, through observations with varying chemical and physical characteristics. So all of this work is motivated by an astrochemical modeling project that I started when I was a postdoc. I had results from my thesis project that didn't make sense. I sat down as a chemist and wrote out a reaction network, and I contacted Eric Herbst, who was at Ohio State at the time, one of the preeminent astrochemists in the world who's a specialist in astrochemical modeling. And I said, Eric, I have this chemistry that we need to put in the models and give it a try. So I actually, in my free time as a postdoc, would drive from Illinois to Columbus and work with Eric's group over the weekend to run this model. It's now my highest cited paper ever in my career, so it was worth it. We actually started looking at these photolysis reactions in ices and the radicals that might form from those reactions and the simple chemistry that could build up from recombining those radicals as a new star forms. In the previous models, what they had done is assumed everything stayed at 10 Kelvin, and then the star turned on and it went to 300 Kelvin and dumped everything into the gas phase. And we put in a gradual warm-up. It seemed obvious, but no one had ever done it before. So Jeff Blake used to laugh this was global warming in space. We put in these radical recombination reactions and very easily, through very straightforward chemistry, built up a network of molecules, all of which had been detected in space, none of which anyone could explain through gas phase chemistry. And the models actually got close to the observations in terms of the relative ratios between molecules. Well, in terms of the overall abundance, but the relative ratios were off. So it was pretty clear that we were on the right track with the chemistry, but that we needed to tweak the reaction network in some ways to get closer to what it is that we're observing. In particular, if you take a look at these molecules that are known interstellar molecules, almost all of them have components from either HCO or from methanol photolysis. When I came along, hydroxymethyl and methoxy were considered to be the same thing in the astrochemical models. And I said, these are not the same molecules, and we split them into two reaction channels and then added all of that new chemistry in. The problem is we had no idea what those branching ratios are. And so this is a huge problem in the field. We still don't know, but we have a better idea than we did when I came on the scene. My group is trying very hard to measure those branching ratios. But if you take a look at what could form from methanol photolysis products in the interstellar medium, you can quickly get to three molecules: methoxymethanol, methanediol, and aminomethanol. Methoxymethanol has now been observed in space. So it seems like we got that one right. The other two don't have laboratory spectra. These are not molecules you can buy in a bottle. Most organic chemists would tell us we're crazy and they don't exist. Aminoethanol was part of my thesis project, but aminomethanol is not stable. Aminomethanol actually reacts with itself and forms hexamethylene tetraamine. So if you have aminomethanol around, it'll go in that direction and not come back. Aminomethanol is predicted to be the precursor to glycine in the interstellar medium. Methanediol is predicted to be the precursor to sugars. So if we can directly get to these two molecules from methanol photolysis products in just a couple of steps of chemistry, that is a big deal for prebiotic astrochemistry. I'm particularly interested in aminomethanol because it is that direct link to glycine. And so I started thinking about ways that we could make it in the lab. And I stumbled across this work where people took matrix isolation studies and they put ozone in the matrix with organic precursors, photolyzed the ozone, made electronically excited oxygen atoms, and then they inserted into CH bonds. This is an incredibly exothermic reaction. And so the products, if they aren't isolated in a matrix, actually dissociate after they form because they're pumped full of energy. But groups actually saw spectroscopic evidence of methane diol formation and methoxymethanol formation through this mechanism. And so I hypothesized that we could use methylamine to get to aminomethanol in this way. And so this has really motivated a lot of the work that's been done in my group in the last decade or so. Aminomethanol, we looked at it computationally, and it turns out that it is indeed the most stable product of this insertion reaction by about 150 kcals per mole, but that there are other side products that could also form that are just slightly higher in energy. And so we're hoping if we do this in a supersonic expansion, where we form the molecules and then expand them rapidly adiabatically into the chamber to cool them down, that we can quench further reactions, we can hopefully quench that excess energy, and we can isolate aminomethanol from that. So taking this all in hand, we went in the lab. We built a very simple direct absorption single pass spectrometer where we shine terahertz radiation. Well, we use RF out of a microwave synthesizer through a millimeter submillimeter frequency multiplier. We shine that through our supersonic expansion. We detect it with a helium-cooled hot electron bolometer detector, very similar to what you would use at a radio telescope, just without the heterodyne capabilities. And then we cross our molecular source with an excimer laser across a fused silica capillary tube where we've mixed the precursor molecule in ozone. So the ozone photolyzes at 248 to make O2 triplet or O2 singlet delta and oxygen singlet D. And then oxygen singlet D reacts in that tube with the organic precursor to make the product. And at 248, most of our precursors don't dissociate. So here's a picture of the system in action. This is our fused silica capillary, and you can actually see the fluorescence on the tube from the excimer laser as it crosses that tube. This was one of those projects where I did a calculation and I assumed a bunch of things, and I thought I had an idea of how much would form, and I figured it would never be that good. I had actually been told before I went up for tenure to put some things on hold, push one project all the way through to completion, and then come back to the rest. So I had told my student Brian not to work on this. Turns out Brian didn't listen and was coming in on nights and weekends and working on this project and not telling me. And then working on the other project during the day. Brian didn't sleep a lot in grad school. Houston can verify. And so Brian actually called me one Sunday evening at about 10 p.m. and said, "Susanna, I have methanol." And I said, "Of course you have methanol. We use methanol as our test for everything in our lab." And he said, no. With the O singlet D project, I have methanol. So he had taken, first we took ozone, we photolyzed it. You can see where the laser pulses, the ozone depletes, and then it grows back in. And then if you flow in methane, the O singlet D, you can see again our laser point here, pulse here, the O singlet D would form after this pulse, and we see a little blip of absorption, of methanol absorption. This was 1 week after Brian started doing experiments. Science usually doesn't happen quite this easily. We were over the moon thrilled about this. So we actually went on then and measured all the methanol lines in our range. We tested it out. We got all of our physical parameters. So you can scan point by point across each frequency, look at the absorption, and use the O singlet D plus methane to make methanol. This is the first time anybody had ever done O singlet D in a supersonic expansion, these sorts of insertion reactions. What we learned very quickly was we weren't just making methanol. It turns out there's so much energy in these reactions that it blows the products apart. So we also saw formaldehyde, methoxy. Brian was thrilled we saw O2 singlet delta, which is the side product from the O singlet D formation. We also saw water in the tube would pick up oxygen and form peroxide. And we saw CO, which means that methanol was completely blowing apart. We can actually, in the lab, measure the relative intensities and back out a Boltzmann analysis, just like we do for space. And so we can calculate a temperature of 11 Kelvin for the methanol that we're forming from this reaction. We also very quickly learned that the chemistry changed depending on where on the tube we put the laser. So if we move the laser further up the tube towards the valve, we actually make more methanol, but we also make more formaldehyde. So side products are a huge problem in this experiment. Both the product being excited energetically and dissociating, but also reactions with the ozone and the oxygen in the tube. And so this is something that we've learned we have to contend with each experiment, and we actually have to re-optimize the position of the laser for every experiment that we do. We quickly also learned that if we run methylamine and ozone together, that methylamine very readily undergoes ozonolysis, and we end up with black goo in our source, which is a problem. And so Brian actually figured out a way he bought a $5 piece of acrylic, drilled holes through it, and bolted 2 valves onto it. So the ozone and the methylamine come through separate channels, and they don't combine until right before the photolysis region. So we eliminated as many of those dark product reactions as we could, but we still see quite a lot of stuff. You can actually see this is discolored from all of the ozonolysis products forming in there. But it actually let us run because our valves stayed stable because we weren't making products in the pulse valve. So when we take methylamine plus oxygen and we do this insertion reaction, these are the 3 things that were predicted to form, amino-methanol being the most stable. These are all the things we've detected thus far. So we see a lot of side reactions in this chemistry. The prettiest spectrum we got was methylamine, which you can see all of the different hyperfine components here. It's really beautiful. But it's hard to sort out when you have a molecule where you have no spectroscopic data to begin with, which ones of these lines are from which species. This is very much like what we do with interstellar spectra, where we have a complex mixture and we have to identify all the different components. We have gone through, this is our product spectrum in the range where we've scanned so far. We targeted this frequency range because it overlaps with our observational spectra. And you can actually see all the different lines. We can go through and pick out which ones are methylamine and which ones are from the other side products that we've identified, but we haven't yet pinned down amino-methanol. We do know that we have those dark products in there, and the way we record our spectra is to watch the signal as a function of time. And so we can actually watch as a function of time, our laser pulse is this red bar here. And so we can actually see which products were there before the laser and which ones weren't. And so we know which ones are dark products and which ones are actually laser-induced products. So we can go through this list, sort the frequencies, and find the lines that are just from the laser-induced chemistry, and that narrows it down a little bit. About the time that we were becoming stumped by this, I had an intern from the Gwinnett School of Math, Science, and Technology, which is one of the highest-ranked high schools in the country. Sam is amazing. Sam came to me as a junior, actually the summer after his junior year in high school, and spent the summer working with my group, and then decided to do an internship during his senior year. So twice a week, Sam would drive down to the lab from his high school and spend a few hours in the lab. As a high school senior, Sam built a spectrometer and took the spectrum. So this is actually a spectrum where we just flowed ozone and methylamine into a flow cell, and we took a spectrum of everything in the flow cell, hoping to be able to identify which of these lines were from ozonolysis products. And it gave us a way to sort through our spectrum quickly. So the second derivative line shape is actually from our flow cell experiment, and then the sticks are the lines from our laser experiment that we acquire one at a time. You can see if it's in both, it has to be something forming from methylamine and ozone reacting. And if it's only in the laser spectrum, that's something that's forming from the O-singlet D chemistry. And so we've gone through now, we've studied all these lines, we've sorted them into dark products and laser-induced products, and Sam is now actually on Friday defending his honors thesis, where he sorted through every possible molecule we could come up with. We did a tour of the organic chemists in our department and took a poll, and he went through everything. It turns out almost all of those dark lines are actually vibrationally excited methylamine lines that no one has yet assigned and put in a spectral line catalog. And this is a problem in interstellar identifications as well. There's a lot of information that never gets published because people analyze the ground vibrational state, and then move on. And so we have a lot of work to do as a field to get things caught up. Sometimes the number of detected molecules goes down because it turns out to be an isotopolog or a vibrational state of something that's already been studied. And I think that's the case here. We do have some lines, however, that don't match up with methylamine that are clearly laser-induced products, and they also have hyperfine splitting, so we know there's a nitrogen in there, and we're pretty sure these are aminomethanol lines. We're having a hard time with the assignment right now. We've done the theory, and we have the lowest energy structure, so we did a prediction. So our spectral prediction's up at the top in red. Our laser-induced spectrum's down at the bottom in black. You can see they don't match very well. And maybe that it's trapped in a higher energy state, some high energy conformer. Harry Gray thinks it's the zwitterion. We've never found any structure that matches this spectrum. It may be a combination of products. We're not really sure what's going on here. But I have a second-year graduate student named Haley who is amazing. And Haley has decided to take it upon herself to redesign the whole experiment. And so in the last year, she's completely redone the source mounting, the laser alignment, all the data acquisition routines, and she's trying to get to the point where she has very precise control over laser position and the timing of everything so that she can control the chemistry better than what we've done in the past. And she recently had an inspiration that if we switched our precursor to N2O instead of ozone, we could make O singlet D, and then the nitrogen's not nearly as reactive as the oxygen, and we don't have to worry about the ozone reactions. The problem is N2O, the O singlet D from N2O actually recombines with N2, and so we really have to be careful with this. But she's done the calculations, and it turns out that our reactions with methylamine and ozone are so significant that it depletes the signal for methylamine by like an order of magnitude. So we think we regain what we lose for O singlet D production by going this way. So Haley this week is running experiments with N2O as the precursor for O singlet D, and hopefully this will sort out the chemistry and we can move on with aminomethanol. So once we have that figured out, we're going to compare to the calculations, hopefully figure out the structure, do the assignment, and then extend the spectrum up to 1 terahertz so that we can actually compare to observations. Methane diol is still of great interest to me. We started with aminomethanol because it has a bigger dipole moment, so it should be easier to detect. Methane diol has a really tiny dipole moment, but the chemistry is easier. So we may switch over to methane diol one of these days and give that a try. And we also want to look at what happens if we start looking at larger molecules. So we want to try to make carbonic acid in the gas phase and see there is a spectrum in the microwave regime, but we would like to take that all the way up into the far infrared so we can look for that in space. In the future, I've been talking a bit with Wade Sisk at the DOE. They're very interested in O singlet D kinetics. And so we're thinking about actually using this as a way to get at the kinetics by changing the length of the tube and the diameter of the tube and controlling the measurements that way. Really, I think to get to aminomethanol, we may have to push towards an increase in spectral sensitivity. I think those lines I showed are probably the strongest lines in the spectrum, but there may be many more that we're missing down in the weeds in the spectrum. And then, of course, observational searches. So I'm going to switch gears now to the astronomy side of things and talk about how we do those observational searches and how this matches back up with what we do in the lab. Again, we have Herschel observations. As a postdoc, I worked for the CARMA array, the combined array for research in millimeter wave astronomy. This was, if you know radio astronomy, the Owens Valley Radio Observatory and the Berkeley, Illinois, Maryland array combined in Northern California and moved to the high site at CARMA. They lost their funding a couple of years ago, so CARMA is no more. But we have a lot of CARMA data sitting on the back burner as well. The CSO, this is the one where I took that picture at the beginning. This is a submillimeter observatory on Mauna Kea on the Big Island of Hawaii. It's also lost its funding from the NSF, and now they're trying valiantly to take the dish to Chile and turn it into a new observatory. So fingers crossed. And then, of course, ALMA in Chile has changed absolutely everything. So when you go outside and you look up at the night sky, maybe tonight it'll be clear enough you can. This is what Orion looks like. In Orion's sword, there's a fuzzy spot. And within the Orion Nebula, that is that fuzzy spot, there's a region called Orion KL, Orion Kleinman Low. It is a region of active star formation where there are multiple new stars of varying masses in this region. And this is known to be one of the hotbeds for molecular astronomy in terms of seeing different types of molecules in space. It was one of the first sources. If you're going to go look for a new molecule in space, you look at Orion and Sagittarius. If you look at this using a interferometer, you can get an image. This is a low resolution image actually from Owens Valley from back in the day. And as our interferometers get better and better, you can get higher resolution images. The CSO on Mauna Kea is a single dish telescope, so you get everything within this yellow circle all in one shot. So we have a complex mixture of molecules, not all of which may have the same spatial distribution, all of which have different temperatures and densities. And it's our job as astrochemists to sort out that complicated spectroscopy mess and try to pull out physical parameters from that. There's a lot of literature about Orion. Jeff Blake, my thesis advisor, did his PhD thesis on Orion. And so there are multitudes of line surveys looking at molecules in Orion. But we decided to start with Orion for this project because we were using a brand new detector at the observatory. And it's always good to look at something where you already know what's going on before you go and look at something new. So we actually took this spectrum. So this is a broadband spectrum of Orion across the whole 1 millimeter band of the observatory. This big line here is carbon monoxide. You can go through the spectrum and there are over 3,000 lines. You can assign about half of them to known molecules that have information in spectral line catalogs. There's two main spectral line catalogs for this. One's managed by the Jet Propulsion Lab at NASA. The other is managed by the Cologne Spectroscopy Group. And so you can go to these catalogs, you can download catalog files, and you can try to match everything up to the spectrum. That gives us about 75% of the integrated intensity, which means everything that's left is much weaker lines from unknown molecules, many of which could be vibrationally excited species or isotopically substituted species. So when I go outside and I see Orion at night, this is what I think of. So you can go through here and pick out, this is a methanol branch. There are dozens of molecules in here. Orion wasn't enough for me. Actually, at the CSO, they tried a lot of new instrumentation at this observatory. The director, Tom Phillips, was an instrument builder, and he wanted to do this sort of thing. And so he would let grad students try out their instruments on the observatory. So there was a grad student at Caltech, Frank Rice, who actually built this new receiver, put it on the telescope, did some measurements on Mars, and then didn't know what else to do with it because his thesis project was to build the receiver. So we had coffee one day with a group of people interested in this area, and his advisor, Jonas Medzina, said, "Hey, Susanna, do you have any ideas for this receiver?" And I was in my beginning of my 5th year in grad school and starting to think about writing up, and I said, "Ooh, yes, I have ideas." So over the course of a decade, we've visited the CSO more times than I can count. I have been to Hawaii at least 36 times. And we collected broadband spectra like that one of Orion, which I show on top, for 32 star-forming regions in our galaxy. So the idea here was to pick sources where we knew there was complex organic chemistry, but we didn't know anything else about the chemistry beyond molecules like methanol, and to cover a range of age, size, mass, and density and temperature to try to see the differences in the chemistry. So I actually stacked these based on methanol intensity. So everything else is multiplied up by a factor of 5 or 10 because Orion and Sagittarius are so bright. And you can go through here. This is methanol. this is methanol, this is CO. You can go through and see the trends. So there should be methanol in everything because that's how we chose our sources. But a lot of these sources haven't been studied at all. And so we were curious as to whether Orion and Sagittarius were unusual. Between the two of them, they have something like 200 molecules detected. And we didn't know if that was common or if they were the extreme cases. So we went through these surveys, and it took us a lot of time on the mountain to collect this information. We also got 42 hours of time on the Herschel Space Observatory during their first open time call for observations to follow up on some of the lesser-known sources at higher frequencies. So Herschel's a space-based telescope. It can see things that are in bands that are obscured by atmospheric water. So these are at 600 gigahertz and 1.1 terahertz, which is really hard to do from the ground. So we followed up with Herschel as well. You can see some of these spectra are really rich in molecular lines. And so the idea is to go through all of this for these 32 sources and try to understand the chemistry and then be able to compare back to the laboratory data. But to do that, you need to analyze it for all the known molecules first, so that you can sort out all of these spectral lines. So this is a challenge. Tradition in the field was you would go to the telescope, and for one source and one molecule, you would collect a handful of lines with very narrow frequency windows, and you'd identify your molecule and go home. And so you would pick your favorite molecule and go and look at that and not worry about the rest of it. The problem was you fit all those lines individually, and then you had to do a Boltzmann analysis on that, and it was very rarely actually a good fit. This is from some of my thesis work where you can see it kind of sort of goes through the data points, but I mean, this is, fitting lines where you don't know what's blended with them, you don't know how to subtract the baseline correctly. It's really a challenge. So you have to go through and do this systematically, but there was not really at the time any software available that could do that. So my group wrote software. So what we did was we wanted a molecule where we could go through and put in catalogs for all the known molecules. It would fit everything simultaneously with least squares analysis, and we could set a line width, a temperature, a density, and a source velocity for each molecule, and it fit every line for that molecule uniformly across the spectrum so that we knew for certain if that molecule was there or not. And so we developed this program that we named GOBASIC, the Global Optimization and Broadband Analysis Software for Interstellar Chemistry. Astronomers like acronyms. So GOBASIC is our software. It's written in MATLAB. You can use it on a computer cluster. So we can do parallel computing. You can import everything in the JPL and CDMS catalogs if you'd like. It goes through a spectrum. You basically enter an initial guess for each of your molecules, and then it goes through in the order that you tell it, and it does least squares analysis one molecule at a time, and then when it gets to the end of the list, it loops back, and it does that iteratively until it converges on a result. The really powerful thing about this, one, is the local thermodynamic equilibrium parameters are set for a given molecule, so it's uniform across the band. And two, we use the pattern search algorithm. So astronomers in the audience, this is like a 5-point. So you pick a center point, and it calculates there, and then it does points and a cross, and it figures out what the minimum is within that cross. It moves to that minimum, and it does it again, and it opens and narrows the cross until it centers in on a global minimum. So the idea is to get something that goes to the global minimum. It does it for all molecules in the spectrum, and we don't have to sit there and fit lines one by one by one. I mean, there are people with Herschel observations that fit 3,000 or 4,000 lines for a molecule by hand and analyze them. I know a postdoc that did that. So, yeah, we were trying to get away from that and take the user interface out of it so that we can make intelligent parameter space guesses as far as the limits, but otherwise just let it run. And it worked really well. So if we go through our observations and we take a look at what we analyzed here, we have a list of molecules up at the top. They're all color-coded. You can barely even see the observational data. So the total is this dark blue, but you can see here because it's a slightly weaker source, so you can see some baseline under here. But for the most part, it's actually done a really good job at matching the observational spectra. We can run a source like Orion in about 15 or 20 days on the cluster that we have access to, and that's with 40 or 50 molecules and all their isotopic variants and all of their vibrationally excited states. And then we go through, of course, by eye and check to make sure it hasn't run off to something crazy. If you have, high noise, it'll run to some really high temperature with weak lines, things like that. So you have to be careful with your data set. But otherwise, it does a phenomenal job of fitting the data. So we went through these 32 sources, and we learned a lot about the chemistry. My very clever student, Lu Yao, figured out how to graphically represent this. So let me walk you through this. So the circles are actually color-coded with the temperature scale on the side. So 700 is dark red and 10 Kelvin is dark blue. And then the size of the circle is dictated by the log of the density of the molecule. So the ones that have higher densities have bigger circles. And so we can actually go through, some of these have multiple temperature components, which is common in these sources. You'll have two different velocities where the source has structure, and one part will be cold and one part will be hot. Methanol almost always has at least two. And so you can see that we actually have some molecules that show up in every single source. So the top row is methanol. That was our way of choosing the source in the first place. So we were glad to see we could actually see methanol in all of our sources. Propyne was a surprise. Propyne is everywhere, every single one of these sources. And we aren't quite sure why chemically. That was not something that anybody had ever picked up on before. So if anybody has an idea, Bob, we should talk. The other thing we noticed is the sulfur-containing species showed up in all of these sources, which is actually, it makes sense because those species are trapped in the minerals that make up the dust grains, and when the star forms, it blows the grains apart and they all go into the gas phase. So silicates and sulfur-containing species should be everywhere. And so from there we can zoom in and look at the more complex chemistry. This is let me go back. Other way. So this middle part is all what an astrochemist would consider complex. So things like methylformate, formic acid, acetonitrile, all of those molecules are all in this middle range. And it's hard to see on the scale when you fit methanol on the box, then it's hard to see the lower abundance molecules. So if we zoom in, we can see there's a whole variety of things that show up. Some of these sources are actually every bit as rich as Orion in chemistry. So Orion's the last line, and we actually dropped it by an order of magnitude so we could fit the circles on the graph. But there are 3 or 4 sources over here with Orion that are every bit as complicated chemically. And these are not things that people have really spent that much time looking at observationally. If we zoom in here, we can see everything with nitrogen in it. The nitrogen molecules tend to be very warm, and they tend to show up in the high mass objects. So these are the high mass hot cores, stars much bigger than our sun, very long time scales. And we don't know what it is, if it's the time scale or the originating chemistry in the cloud that dictates this. But we see over and over again that nitrogen-containing species tend to show up in the gas phase in high mass hot cores. And this is the first unbiased survey where we actually can show that definitively outside of something other than Orion or Sagittarius. If we go on from there, the oxygen-containing species tend to be much colder, and they also tend to show up in the high mass hot cores, but they also show up, some of these objects are very, very young objects where there may or may not even be a star yet, and yet there are oxygen species showing up there. These objects in the middle are low mass hot cores, or as they're dubbed, hot Corinos. They are solar type stars, so the size of our sun, where the time scale is really short for the warm-up phase, and so you don't get as much chemical complexity in these sources, and they tend to be much smaller spatially, so we actually don't see much chemistry from those sources, which was a disappointment. Some of these over here have some pretty big molecules, and these are all sources that are just shocked regions. There's no star formation. So molecules are coming off of the dust grains with or without active star formation in some of these regions. Probably the biggest surprise of the whole survey is it took Lou Snyder from Illinois, I think 25 or 30 years to confirm the detection of acetone in space. We found acetone in 4 of our 32 sources. And so we were really excited by this because this is not something we really anticipated. The chemistry of acetone's not understood very well. If you zoom in and you look at the spectra, it's embedded under a bunch of other stronger molecules, which is probably why it hasn't been seen very much before, but there's acetone out there in lots of sources. If you take a look at a source like Orion and you do an imaging study, now I'm going to show you higher resolution maps. So if you get more telescopes in an array, you get smaller pixels on the object, and so you can start to understand the structure. And what it turns out that, again, ethyl cyanide in the green shows up in the warm regions. So this upper region in this source in Orion is actually the hot core. This region is what's been called as the compact ridge. This is a region where we think shocks came out from the new star and peeled molecules off of the grains. Methylformate shows up down there. Ethyl cyanide shows up at the core. The weird thing chemically is acetone bridges the gap between the two. Acetone kind of overlays both of them. So modeling-wise, this gets really complicated because how do you model something where you're looking at a kinetics database and you've got ethyl cyanide in one area, methylformate in one area, and acetone kind of bridging between the two of them. So we're actually getting to the point where we need hydrodynamic models with the chemistry embedded in them to be able to fully understand these objects. But it gets better. So we decided to follow up on this observation. So yeah, for reference, the CSO beam sees all of that. So in that Orion spectrum, all of those are superimposed. So if you take a look at this from a physical perspective, Doug Friedel and I decided when we were intrepid postdocs to take a series of karma maps where we used methanol as a thermometer, and then we overlaid the other molecules on top of that to try to see what it could tell us about the temperature. So the heat map in the back in color is methanol, and you can see ethyl cyanide traces the warm regions and methylformate traces the cold regions. And so the temperature is clearly connected to the chemistry in these objects. And the warmer the region, the more nitrogen-containing species that we see. Things are getting even more interesting now as the field progresses because of ALMA. So this is Jeff Blake's thesis project. It took him 27 nights with one telescope in Owens Valley to take that Orion survey. At the CSO, we did it again in 4 nights with an order of magnitude better signal to noise. That was fun to go back and tell Jeff after that observing run. ALMA can do the same coverage with full spatial resolution in 1 minute. So again, 300 terabytes of spectra a week are coming out of ALMA. I may never have to apply for time again if I'm just patient and I wait. Somebody will observe everything that I'm interested in. That's not true. I'm going to apply. They're due next month. So at full capability for ALMA, you can get the spectrum to the same signal to noise that we had in 1 minute of integration time, and you get a map like this. So this is what Orion looks like with ALMA. This is methylformate, and there's about 27 different point sources embedded within that inner region of Orion KL that we could never resolve before. So we have a huge challenge in terms of both data analysis and in terms of modeling to be able to wrap our brains around this, because this is not, it's complex mixtures plus broadband spectra plus complex spatial resolution that tells us something about the dynamics of the source. So this is where astrochemistry is going. So things coming up. We do have those 42 hours of Herschel data I didn't even try the high frequency results until we got the lower frequency ones analyzed, which meant we had to write the program to do it. So we're working on that now. We have preliminary results on those, these objects here. Karma, we still have, I think we may publish the very last maps ever taken on Karma. I think we might have been the last track. We were begging for time at the end. So we have 3 sources that we've covered with Karma, where we have images. They won't be as good as what ALMA can do, but they'll still tell us something until somebody follows up, hopefully me, with more time on ALMA. Cycle 7 proposals are due next month. My group is frantically writing. So the hope is to go back and get spatial distributions of all of these molecules, because without the maps, we have no idea how to account for the different source sizes and the morphology when we do the analysis of the spectrum. So that's really the next step. I've also been really involved with collaboration looking at organic molecules in protoplanetary disks. And we found methanol, and groups are just, every time somebody observes a disk now, there's a new molecular detection. So it's really exciting because we can start to look at how you feed this material into planet formation. Compare back to the models. So once we sort through all these observations, we need to go back to the models and try to figure out what we got right, what we missed, and where we need to fill in gaps. And then, of course, isomers, conformers, vibrationally excited states. There's a lot of work left to be done. So we have things to do. So this is my group, and I have to give credit where credit is due. Lu Yao is the one that wrote GOBASIC. He also did laboratory work. He's now at Lille doing a postdoc with Roman Moitienko. Brian is the one that went on his own and did that O-singlet-D project. He's a postdoc in RIN with Ian Sims. Morgan picked up the O-singlet-D after Brian. Morgan has a chronic illness and got very, very sick in her second year in grad school and decided to leave with a master's. She came back and ran our Gen Chem lab prep operation for 2 years, got herself healthy, and she is leaving next week to go to Leiden to do a PhD with the Leiden group. And I'm both sad and proud. And so the 3 of them are really the ones that drove most of the science that I showed you. This is my current group. Kevin is a 4th year. I have a 1st year Chase, and I have 3 amazing 2nd years right here, all of whom are gearing up to take some of these projects to completion. Haley is the one that's redesigning the O-singlet-D. She's really done amazing things. And Alec, I can't operate without Alec. So Alec did his undergrad with me. Went off to grad school at Boulder and worked with Veronica Vida, got his PhD last year, and then came back. And he's amazing in every possible way. So we're really thankful that he's back with us and having a great time in the lab. So with that, I want to thank my funding agencies and thank you for your attention.